It's my pleasure to introduce Yves André from Sorbonne University, and he's going to speak about the Bettmap.
Thank you very much for the invitation. So, my topic is about a fundamental tool in Diophantine geometry, but fundamental, but recent and a little bit confidential. So, usually, when you see this expression Bettmap, it's well, it's buried in under some technical things. It's written that it is fundamental, but it is not told why it is fundamental. So I would like to put some to highlight this notion in this talk. But first of all, maybe I have to draw landscape of Diophantine geometry to make more precise the role of this Bettmap. So Diophantine geometry can be argued to start with André because of course before there was Diophantus and Diophantine analysis, but the emphasis on geometry, so Diophantine geometry, and it was probably Weil who transformed this field from an analysis to a geometry. So he introduced the notion of height of rational points of algebraic varieties. And this notion remained for a long time the only proper concept of Diophantine geometry. And he introduced not only the concept, but also the machinery. So the machinery goes as follows. So you have an algebraic variety defined over the algebraic numbers, and a line bundle, a class of a line bundle on it, and you associate to this pair a height, which is kind of a function from the algebraic point of the algebraic variety x to the real number, but up to some bounded function. And this is machinery because there are many functoriality and positivity properties which are quite useful in this field. Sometimes it's a bit annoying to allow some ambiguity, some bounded function, and it is important to normalize the height. And there are two famous cases: the Nérontate height, denoted by cap hx, when x is an abelian variety. There is also fiber-wise variant for an abelian scheme with a symmetric, relatively ample line bundle. And the other fundamental example is the Falting's height of abelian varieties. So Falting height for a point in a modular space for abelian varieties. Okay, let me recall two apex of this first branch of Diophantine geometry. I will argue that there are two branches now of Diophantine geometry: the older, which is a study, classical one, a study of rational points, and a newer one, a younger one. So for the first branch, of course, maybe the most famous result is model conjecture proved by Falting's theorem. So if you have a smooth projective curve of genus bigger than 1 over a number field, then the number of rational points is finite. In Falting's proofs, this uses the Falting height as a main tool, and in a later proof by Wojta, the emphasis is more on the Nérontate height, on the Jacobian of the curve. Second result, very famous, is the Bogomolov conjecture, proved by Ulmo and Zangs in 1908. So if A is an abelian variety over Q bar, and if X is an irreducible closed subvariety, which is not contained for simplicity in any proper algebraic subgroup of A. Then there exists some epsilon, positive constant, so that the algebraic point in X of height, Nérontate height, at most epsilon is not Zariski dense in X. So this is a kind of goes beyond the minimum Ford conjecture. So this branch of Diophantine geometry is still vivid, of course. It has grown up around questions of effectivity, uniformity, and so on. So, but let me speak about the younger branch, which is a branch of the theory of unlikely intersections. This younger branch grew out of some series of conjectures, Manning-Mumford, André Hort, and Zilberpink, and other similar conjectures. And typically, in this theory, one considers a countable collection of subvarieties, which I denote by Z alpha, of a given algebraic variety X, defined over a field F of characteristic 0, and one looks at the union or at the intersection of this Z alpha. So this is different from the situation of algebraic geometry because we have here a countable collection and not a finite collection. And unlikely, in the unlikely intersection, refers to phenomena which occur precisely because the collection, the alpha, is infinite, while a standard algebraic geometry would rule them out if the collection were finite. So to be more precise, the usual context is the following. So X is actually a subvariety of an ambient variety, let's say Y, in which there is some notion of special subvarieties. And one is looking for is either the union of all special subvarieties of Y which are contained in X, or the intersection of all of X with some special varieties. Maybe it's not properly written, but I hope it's clear what I mean. So this field developed a number of new tools. It's a rather recent field. And a number of these tools come from logic, from tame geometry or O-minimality. And to begin with, the Pila-Wilkie counting theorem, which was imported in Diophantine geometry in a paper by Pila and Zanier. So it's called the Pila-Zanier method. Another tool, which relies, in fact, on the first one, on the counting theorem, is the functional transcendence. Lindemann Schanel type theorems, which are very powerful theorems developed over the years, in recent years, and all relying on this counting theorem. And the framework in which this functional transcendence operates is a framework of bi-algebraicity. So you have a kind of a uniformizing map between two semi-algebraic variety, but the map itself is transcendental, and one compares given an analytic subvariety on the top, what is the Zariski closure and its dimension on the top, Zariski closure on the bottom, and the bi-Zariski closure, which means the smallest subvariety, which is algebraic on the top and on the bottom. But there is another tool, very important tool, which is independent, but which nevertheless has some ties with the other tools. It is a Bettmap, which was introduced different guys by masters and here and other people, and was first systematic study probably occurred in our paper with my paper with Corfay and Zanier, published only last year, so it's recent. So, but this will be my main topic in this talk. But before beginning, let me make a remark that this powerful method of this second branch, unlikely intersections, are reshaping the Diophantine geometry. They are displacing its frontiers. For instance, one witnesses growing influence of this younger branch, unlikely intersection, on Hodge theory. And it was already clear in Bruno Klingler's talk last week. Also, one remarks that the restriction to varieties defined over Q bar, which was of course typical before in the main branch of Diophantine geometry, Diophantus, is no longer a distinctive feature. But still, this branch in spirit remains strongly tied to the circle of conjecture it began with. And moreover, we will see that a unification with the older branch, that is the study of rational points, is in progress around questions of uniformity, and this will be the topic of the end of this talk. So let me give some general example of unlikely intersection problem. So let us start with an abelian scheme A to S, defined over the complex number, and relative dimension G. And let us consider a section from S to A, denoted by Xi. By definition, the torsion values of this section are just the inverse image by Xi of the torsion point in this abelian scheme. So this is isomorphic by the torsion point intersected with the image of the section. So the torsion section, the torsion point are, of course, countable union of subvarieties of A, and we are intersected this countable union with an algebraic subvariety. So this is a typical unlikely intersection problem. Why unlikely? In fact, it is sometimes likely, sometimes unlikely, and there is a dichotomy, heuristic dichotomy, which says that under some natural non-degeneracy condition, which I make clear in the sequel, one expects the following dichotomy. So either if the dimension of the base of S is smaller than G, then the torsion values should be algebraic. So there should be, in fact, integer n, so that's all torsion values are in fact n torsion values. Or if on the contrary, the dimension of S is larger or equal to G, then the torsion values are expected to be dense for the analytic topology of S. This is a very sharp dichotomy, which is typical of the field of unlikely intersection. and which has little to do with standard algebraic geometry. The point is that A tor, the torsion, is a countable union of algebraic subvarieties. So let me give some very concrete example of this, maybe three examples, concrete example or illustration of this problematic. So the first one is very classical. It's from the beginning of the 19th century. It is about the Poncelet game. So we give ourselves two conics, different conics, C and C prime. And we take first a point, P0, on the first conic, C, and also a line, L0, which passes through P0 and which is tangent to the other conic. So there are two of them. We choose one. So we start with P0 and L0, which contains P0. Then this line cuts the first conic at another point. Let us denote it by P1. So we can iterate the process. So we have Li, a line, Pi, a point in the line. The line is tangent to the second conic, contains a Pi. And we denote by Pi plus 1 the other point belonging to C in Li. And then, starting with this point, we can construct the other line, which is tangent to the second conic and contains this point Pi plus 1. So there is this two-step move, and we can iterate. And the game ends when one comes back to the initial situation, L0, P0. This is a theorem of Poncelet that the game ends or does not end independently of the initial data, L0, P0. Depends only on the pair of conics. Let me sketch a proof given a little bit later by Jacobi. Jacobi considers the incidence curve. So incidence curve in a C Church cross C. C Church is a dual curve, so the line which are tangent to C. So the incidence curve is given by the set theoretically as a set of pairs of L and P, where L is a line on C tangent to some point, tangent to C. So it's a point in C Church, and P is a point in L. And simple analysis of ramification shows that this incidence curve is of genus 1. Hence, it is a torsor under an elliptic curve, which I denote by A. Now, this process, this two-step process from Li, Pi, Li, Pi plus 1, Li plus 1, Pi plus 1, is a composition of involution on the genus 1 curve, on the incidence curve. Hence, this corresponds to a translation by some point, xi, of the elliptic curve A, which is independent of the initial data. This does not depend on this. This is just a general process on this. And clearly, the game ends if and only if the point xi is a torsion point. So that's Jacobi's proof. But now let's complicate a little bit the game and imagine that the pair of conics, C and C prime, move. Then up to isomorphism, this pair, the parameter space of such pairs up to isomorphism is in fact an open subset in the projective plane, because you can fix the first conic and then you have the second one, which is given by 3 parameters up to homothéty. In this case, when you move your conics on the parameter space S, the elliptic curve A from before is replaced by an elliptic scheme A to S, and the point Xi is replaced by a section. But in this case, the dimension of S is 2. So, and 2 is bigger than G, which is 1. And so it turns out, in fact, one can prove that one is in the second case of the dichotomy which I mentioned. So the torsion values are dense in the parameter space. In other words, for almost all pairs of conics, the Poncelet game ends. One can complicate the game in another way. One can consider simultaneous games with, for instance, you fix the first conic, two first conic, C1, C2, and move only the second one in a pencil. Then in this case, the abelian variety, the elliptic curve becomes an abelian surface, A cross A, and it is, so the parameter space is restricted to a line in S cross S. And so, because the dimension, for dimension reasons, one expects in this case that there are only finitely many such C prime in the pencil, so that the simultaneous Poncelet game ends. Another example, K3 surfaces and curves on K3 surfaces. The classical topic is the topic of rational curves on K3 surfaces. And if curve C is rational on K3 surface Y, of course, any 2 points are rationally equivalent on Y. But there are other cases, other curves C, which have this property. They are a little bit mysterious, and they are called constant cycle curves. To describe them, this tentative, we can consider a very ample divisor on the K3 surface, let's say D, and the universal curve on this linear system. Then we rest to the regular locus, and we consider the Picard scheme, or the relative Jacobian, so the pullback of the Jacobian fibration. Then we can define a section of this abelian scheme over S by the following formula. So if you start by a curve, a point on this curve, you can associate it to this pair Xi of S, which is given by a point in this Jacobian, which is just the self-intersection of D. D is a very ample divisor on Y, time X minus the restriction of D to C. So this is degree 0, so point A. And one can show that the torsion value locus of this section is one-dimensional. One conjecture, furthermore, that this locus in fact projects via the obvious map from S to Y to a countable union of constant cycle curve C. So one expects, especially, that there are many curves which have the property that any 2 points are rationally equivalent, whereas the curve is not necessarily rational. Another example, which is more number theory, number theoretic, another illustration of this kind of thing. So there is a famous dichotomy related to the question of confinement of real algebraic integers. So the dichotomy is the following. So the first case, proved by Fekete and Sege, is that if you have two real numbers, a and b, a less than b, and if the difference is less than 4, then there are finitely many algebraic integers whose all conjugates are in the interval a, b. And in the opposite, the theorem of Robinson, Raphael Robinson, if the length b minus a is greater than 4, then there are infinitely many of those. In fact, Robinson even generalized this second point to the case of union of disjoint interval ai and bi. And the key point of his proof is to introduce a hyperelliptic curve C with a fine equation y square is the product of x minus ai, x minus bi. So these are the extremities of the intervals. He introduced, of course, is Jacobians, viewed as an abelian scheme parameterized by the space of all tuples of ai's and bi's. And also the section psi. This is so there are 2 points at infinity. This is hyperelliptic curve. Infinity plus minus infinity minus. So I refer to Serge Bourbaki talk on this topic. Now the main point to prove Robinson theorem, which is a theorem about there is an infinity of such numbers, is that the torsion values of this section, this abelian scheme, is dense in the space of parameter, even in the real points. Now let me come to my main topic, which is the Bettmap. The Bettmap is a natural tool to study such kind of questions, and many others in the cadet branch of unlikely intersections. So the setting is an abelian scheme, A to S of relative dimension G, with a given section Xi from S to A. The Bettmap of this pair, A and Xi, will be a real analytic multi-valued map from the complex point of S to the real space dimension 2G. So this is not at all the kind of maps one is used to encounter in arithmetic geometry or algebraic geometry. So let us start with the simplest case when S is a point. So when we just have an abelian variety, then this map is just a point in R to G. And this is just given by the coordinates of a point of a complex point of A, viewed as a torus, in a mesh of the lattice H1 of A. Of course, this is ill-defined, so this is multi-valued. It depends on the choice of the mesh. Important point, which makes tie with the previous discussion, is that these coordinates are rational if and only if Xi is a torsion point. So now let us turn to the general situation of an abelian scheme. And let us denote by gamma the maximal normal subgroup of the fundamental group of S, which acts trivially on the H1 of some fiber of abelian scheme. And let us denote by S gamma the quotient of the universal cover of S by gamma. Then on S gamma, there is a real analytic splitting of the abelian scheme, pull back to S gamma. like this, S gamma times something constant, and the section is given in this decomposition by some map beta gamma, beta subgamma, from S gamma to this torus. And this leads to a real analytic multi-valued map from S to R to G, so to the H1 of ASR, which is identified to R to G as the choice of the mesh of the lattice of AS. So this is the Betti map. And it has complex analytic fibers, but it is itself only real analytic and multi-valued. Now, the same remark applies. If you consider the pullback by beta of the point with coordinate in Q, rational point in R to D, then this is nothing less, nothing more than the torsion values of psi. Therefore, if the dimension of S is at least G, and if beta is generically submersive, then the torsion values are dense in S. So this is a relation between our problem, density of torsion values, and the Betti map. Here, generically submersive, if the dimension of S is at least G, just means that the rank of the Betti map is 2G, rank in the sense of differential geometry, so the rank of derivative, of the derivative. So some remarks are in order here. The first case was considered by Manin, in fact, when proving the Mordell conjecture in the function field case, that in this very special case when the rank, so the rank of the Betti map is 0, correspond exactly to the case when the section is torsion. This is a long story, there is a mistake in the proof. It was corrected several times with introducing several new mistakes, but finally, well, it believes that well, one has a correct proof of this. Second remark, let us look at the monodromy of this map, beta gamma, from gamma to the H1 of A. Then there is a null theorem of mine that if you assume a standard condition that the abelian scheme has no fixed part, and moreover, if you take the integral multiple of the section, it is Zariski dense in A, which means essentially that psi is not contained in any upper algebraic subgroup of A. The conclusion is that the image of the monodromy of this map is Zariski dense. By the way, it's still an open question to know whether or not this image is a subgroup of finite index of this lattice. This is a very difficult question, in fact, which is related to a congruence subgroup problem, but I leave it apart. So, of course, one cannot expect any direct relation between the Betti map itself, which is only multi-valued and real analytic, and classical maps, which one knows in algebraic geometry or arithmetic geometry. But the point is that here, what is relevant is not the Betti map itself. It is its generic rank. So the generic rank of its derivative. And because of this, it makes sense to compare, for instance, the rank of the derivative of the Betti map and the rank of the Kodaira-Spencer map attached to the abelian scheme, or better, to the one motif attached to the abelian scheme and the section. But let us leave this aside. So the Kodaira-Spencer map, there are several variants, but one of them is a map. Let us assume that S is affine for simplicity, theta, from the tangent space of the base S to the tensor product of Li A to Li A dual. So that by contraction, any invariant relative 1 form omega provides a map, which I denote by theta subscript omega, from the tangent space of S to the Lie algebra of the dual abelian scheme. Then the correlation between the Betti map, or rather between its rank and the rank of Kodaira-Spencer, is the following theorem under the same condition as before. If for some omega, the rank of this map is G, so maximal, so to speak, then the rank of the Betti map is also maximal, is also 2G. I have no time to give the proof, but the proof is rather funny in the sense that a priori the fact that beta is only real analytic is a drawback. So we are not accustomed in arithmetic geometry to deal with such map. But we take advantage of it by using a double action of monodromy on the holomorphic and on the anti-holomorphic part. So this gives us much more degree of freedom. That's the principle of the proof. So to go further, one needs a stronger result, and this result comes from functional transcendence, and they use O minimality, so tame geometry, and axe Schanel tap. So let me state a theorem, like Corvaya, Gao, Sanier, and myself. Let us make some assumption like non-trivial endomorphism, that the dimension of, let's say, the base of the image of the base in the moduli space variety is at least G, so where in the second case of my dichotomy of the beginning, and that the section is non-torsion. Then the conclusion is that in this case, the rank of the Betti map is maximal, is 2G, and a fortiori, as I told before, the torsion values are dense in the base. So the proof uses 3 ingredients. First, the 2 assumptions that there are no non-trivial endomorphism, and that the dimension of the base is at least G, implies by an analysis of classification of Chinois varieties that this base is not, so image of the base in AG, modular space of principally polarized abelian variety, is not contained in any special subvariety. The second point is a refined analysis of the previous theorem about relation between Betti map and the Kodaira-Spencer map. And under the assumption, by contradiction, that the rank is not maximal, one can find an analytic subvariety, Z, of the Ziegel space, embedded in its compact dual, which is an algebraic variety. And Z lies above S. The dimension is D minus D plus 1. And the dimension of its Zariski closure in this compact dual is at most the dimension of AG, so G plus 1 over 2 minus G. But then the third part of the proof is that it contains this assumption contradicts the Schanel theorem, as demonstrated by Mock-Pilar-Zimmermann in the hyperbolic bi-algebraic situation. This Schanel theorem is an inequality between some dimensions. So one has Z. This is a bi-algebraic situation. One can see Z as a subvariety not only of HG, but of the product AG and HG Czech, which are both algebraic variety, but Z is analytic. Then the theorem says that when one considers the dimension of Zariski closure of Z in the product, it is at least the dimension of Z itself plus the dimension of Z by ZA, it means the smallest algebraic variety, which is both algebraic on the top, so in HG Czech, and in the bottom on AG. And here, because if one put everything together, because of this plus one, there is a contradiction here. But you see, we have used this theorem, which related, it was a weak relation between Kodaira-Spencer of the abelian scheme, but without regarding the section, and the Bettmap. So it's not optimal. And by using a mixed version of Schanel, Gauche later obtained the optimal statement. It's complicated to say. So let us move forward and discuss the notion of non-degenerate subvarieties of an abelian scheme. So again, A to S is an abelian scheme of relative dimension G. And this notion, introduced by Habecker and Gauche, is one of the most important applications of the Bettmap in Diophantine Geometry. And it goes as follows. So, it refers to a subvariety, a closed subvariety, X of A, of dimension less or equal to G. And so to define the notion of non-degeneracy, one look in a different way to the Bettmap. So there is no get rid of the section. So one looks at the Betti foliation. The Betti foliation is just a map, a real analytic multi-valued rigidification of A viewed as a fixed torus. So from A to torus or to G over the. So this is essentially the same construction as before, except that there is no section here. But still, this is essentially the same thing. Because if you have a subvariety X of A, you can perform the base change from S to X, and then you get a section. And then this B restricted to X is the same essentially than the previous Bettmap, beta. And conversely, if you start from an abelian scheme with a section Xi, you may take here in this framework X, the image of the section, and then again the Bettmap, the two Bettmap essentially agree up to some integers. So now the definition is that a subvariety X is of an abelian scheme A of S is non-degenerate if the derivative of this second Bettmap, so restricted to X, has generically maximal rank 2D. That is, if B restricted to X is generically immersive. So now, in the first part of my talk, I consider the problem. This is always the problem of maximal rank, but in the first part of my talk, maximal rank meant generically submersive. Here, this is generically immersive. then one can analyze the locus where the rank is not maximal, and one, in some simple case, one finds that it is constituted by special subvarieties, torsion cosets in fiber, if you prefer. The important point is that the heuristic meaning of non-degeneracy is that this is a kind of substitute of bigness for some appropriate line bundle, which is essentially the polarization restricted to X, to the subvariety X of abelian scheme. So now let me discuss, I promise, some case when the two branches of the Diophantine geometry meet. In fact, the first branch about the study of rational point, and the second branch about unlikely intersections, and underlying the role of the Betti map. So the first situation is the case of the geometric Bogomolov conjecture. It is the following. So kind of a relative version of the Bogomolov conjecture, which I recall at the beginning of the talk. So instead of abelian variety over Q bar, I consider now an abelian scheme over Q bar without fixed part for simplicity. One considers the fiber was Nérontate height associated to symmetric relatively ample line bundle. And one considers a close irreducible subvariety of the total space of this abelian scheme, which is not generically contained in any proper algebraic subgroup. So the situation is the same as in the Bogomolov conjecture, but it is relative to a base S. And the theorem, which is quite recent, due to Cantar, Gauche, Habegger, and Thier, is that for some, this is essentially the same statement, for some constant epsilon, positive constant, the set of points of X, of algebraic point of X, of Nérontate height less than epsilon is not Zariski dense in X. So this relies upon a height inequality à la Silverman, which is the following. So again, A to S, so it's an abelian scheme. X is a closed subvariety of A of dimension D, which is less or equal to G, so relative dimension of the abelian scheme, as before. And HS is the height on S, positive height. Then the theorem, due to Dimitrov, Gauche, and Habegger, is that you can compare two heights, namely the Nérontate height of a point on A and the height in the sense of HS of each image in S. In fact, there is a lower bound like this. There are two positive constants, so that the Nérontate height is at least C HS of the projection of point X to S minus C prime. But not everywhere. For every X where the Betti map has maximal rank. Betti map restricted to X has maximal rank 2D. And in fact, this is in this context that so the Betti map occurred in not only in unlikely intersection problem, but in the direction of study of rational points. Another situation where the two branches of Diophantine geometry met recently is a uniform Mordell conjecture. So I mentioned Mordell conjecture at the beginning of the talk, and the setting is the same, a smooth projective curve of a genus bigger than 1 over a number field, but the uniformity refers to say something about the cardinality of the f rational point of this curve. A very recent theorem due to concatenation of two results of Dimitrov, Gao, Habegger, and on the other hand, Kuhne, is that this number is bounded from above by some constant which depends only on the genus of the curve, G, up to the power 1 plus the rank of the Jacobian, of the f point of the Jacobian of C. This is a group of finite rank. So the approach here is Wojta's approach, but with 3 ingredients. The first one is the geometric criterion of non-degenerate subvarieties applied to the universal Jacobian. So it moves this curve C in a universal family in MG. So. And, but it is not enough to do this. One has to use some well-known efficient construction due to Falting and Zhang to study what happens to non-degeneracy. In fact, this construction improves non-degeneracy. The second point is the height inequality and a Silverman, which I mentioned before, on any given non-degenerate subvariety. And the third point is an equidistribution result, Ulmo-Zhang, if you want, which is due to Kuhne, on any given non-degenerate subvariety. So all in all, you see that the 3 ingredients use in a fundamental way the concept of non-degeneracy, which is defined in terms of the Bettmap. In fact, I should say that the theorem of Dimitrov, Gao, Habegger, and Kuhne is much stronger. In fact, they deduce it from a uniform model Lang conjecture for curves embedded in their Jacobians over any field of characteristic 0. So this has nothing to do with Q bar. Thank you for your attention.
Thank you for the beautiful talk. We'll thank our speaker. Questions? There was one question in the chat box from a while ago. There was this slide where you referred to a Bourbaki talk of Serre, and in the chat box, someone was asking which Bourbaki talk of Serre that was.
Probably the last one. I think the title is distribution of eigenvalues of Frobenius, something like this. So. Distribution des valeurs propres de Frobenius, I think. So it was maybe 5 years ago or something.
Thank you.
I have a question, or I have a few questions.
Mm-hmm. Yeah, go ahead.
Yeah. So one thing, can you hear me?
Yes. Now, yes. Mm-hmm.
Okay. So one thing is, why is this map, the Betti map, going to the real torus of dimension 2G? It's called the Betti foliation. Does it actually give a foliation of some form?
Yes, it gives a foliation actually, and the leaves are complex analytic. The map itself is not complex analytic. So
it gives a foliation on what space? On the abelian scheme, or?
Yes, exactly. Yes.
Okay. And also another thing I wanted to ask is about this theorem of yours with Kovaya, Gao, Zanier. Why do you need to assume that the endomorphism has no CM? Is it not true if there's CM?
As far as there is a general theorem, it was just it's not the optimal theorem. This assumption, together with the fact that the dimension of the base is at least G, implies that the image of the base in the moduli space of abelian variety of AG is not contained in a special subvariety. So it's big enough. It's not contained in a proper special subvariety. This is by classification of Shimura varieties, but you can avoid this if you use stronger result on the side of Schanel. So if you have at disposal a mixed version as Gauche proved later, so then you can dispense with this assumption.
So are you saying that you can prove an analog of this theorem without assuming that the endomorphism ring of the abelian variety has no CM?
Yes, there is an optimal conjecture. And it's proven now by Gauche.
It's a conjecture proven by Gauche, you're saying? Okay.
Yes. So there is no mystery. The optimal statement is known now.
Okay. Is this a recent paper?
I put it like this for historical reason, and also because this is concrete. So maybe the general statement is a bit more complicated.
Okay. Well, which paper of Gauss is this? He has several papers, right?
Yes, but they are all very recent. So
is it the one on Betti, on the Bettmap? He has a paper on, I think, Bettmap for abelian schemes or something. Maybe
I could not tell you right now the title of the.
Okay, it's okay. I will.
One of his paper in the last 2 years anyway. Huh?
Yeah. Okay, thanks. Yeah, maybe other people have questions. I will let them, or I will wait until we stop the recording.
Any other questions, anyone? I don't see anything in the chat box either. It was a beautiful talk, really beautiful talk. I would have to go over the slides myself later and and try to digest this. Very nice, very nice. And
thank you.
It's clearly a very powerful machinery. So if there are no more questions, we'll thank you again, and